Great, thank you. Can everyone hear me? Yes?
Yeah.
Okay, great. Yeah, apologies to people in the room. I decided to go with the majority and go over Zoom. So I'm going to be talking about some joint work with Nima Anari, Kwikwi Liu, and Cheyenne Oveis-Garon on log-concavity, something called matroids and expanders. And just to start off on sort of a high level, what I want to do is, to a discrete probability distribution, in fact, a finite probability distribution, I'm going to associate a sort of generating polynomial. So really, in this case, in almost all of my examples, we're doing is so by probability finite probability distribution, I really just mean oh sorry, this should be n to the n tuples of non-negative numbers. Let's see if we can fix that. Finite collections of n tuples. And in many of my examples, in fact, this is just going to be subsets of 0, 1 to the n vertices of the cube. Associate a non-negative number to each element of my collection and sort of always rescale so that these non-negative numbers sum to 1, and I get a probability distribution. I can sort of trivially associate a polynomial to these with non-negative coefficients. And the real magic of doing this happens when you can relate properties of the polynomial as a polynomial or as a function with properties of your distribution. And so that's sort of the story that I want to talk about. But that's the high level. For example, so if I took one nice distribution I can take on subsets of 1 through n is I can take a d by n matrix where I'm thinking of d as smaller than n. So I take a short fat matrix. And then to every d by d minor, every collection of d things from 1 through n, I can take the corresponding d by d minor, take its determinant and square it. I get a non-negative real number and use those as coefficients for my polynomial. And just index them by square-free monomials of degree d in the variables x1 through xn. And this gives some distribution. And one reason that one might like such distribution is that one thing that it does is that it favors collections of subsets of vectors. I can think of the columns of this matrix M as the ground set, and I'm picking subsets of these columns. And the bigger this number is, this determinant is, the more likely I am to pick that subset. And so in some sense, this distribution will favor collections of vectors that are well spread out. Another reason to sort of like this setup of associating polynomials and distributions is that one has sort of lots of operations that naturally occur on both sides. So for example, if I took again a polynomial with square-free monomials, so whose monomials just correspond to subsets of 1 through n, and then I took its derivative with respect to some variable, then what happens? All of the terms where say xi doesn't appear, they get killed off. And for all of the remaining terms, I keep them, but I remove the variable x of I. And so this is, on the one hand, a natural operation if we're thinking of a polynomial as a function, taking the derivative with respect to some variable. But it's also a natural operation on the level of probability distributions. Namely, what am I doing if I, again, sort of imagine rescaling so that the sum of the coefficients is 1, then I'm keeping everything proportional, but I'm throwing away everything that doesn't, all of the subsets that don't contain my favorite element I. And so taking a derivative sort of on the polynomial side corresponds to conditioning on the element I belonging to my subset on the sort of probability distribution side. So this gives us sort of a nice dictionary between these two things. And it's sort of surprisingly useful. I mean, if you think about sort of generating functions, like this is not a new idea, but it's a surprisingly sort of useful and beautiful idea.
Do you rescale the measure after this?
Sorry?
Do you rescale it, the measure after this? Because now the sum of the coefficients is not 1.
Yeah, so I'll always rescale so that the sum of the coefficients is 1. So I'd be a little bit lazy with this.
Yeah.
But always sort of consider the scaling with, so that makes all the coefficients. And that's the distribution. Yeah, thanks. And so, from a class of distributions or polynomials, we might want many things. The things that we're going to want in my talk today are that that we might want them to be closed under some natural operations, where natural might come from either the polynomial or the distribution side of things. From the distribution side, we say like conditioning, maybe I want to marginalize. There's lots of things we might want to do and stay within whatever nice class that we're in. If we're going to care about it, it should include some important examples that we like and actually want to work with. One nice thing that one might like is that there's some commonality in terms of the shape of the distribution, where I'm going to keep that fairly vague, but we can understand somehow the geometry of the distribution. And then another thing we might want is to be able to, if we know that we have a distribution in some class, we want to be able to efficiently sample from it, or maybe efficiently approximately sample from this distribution. So we might want some sort of algorithms associated to this class. And so what I want to talk about today is sort of a special class of distribution and polynomials for which we have many of these things. Okay, and it comes from on the polynomial side from sort of functional log-concavity of a polynomial on the positive orthant. So it's a very coordinate dependent thing. So I'm going to take a polynomial with non-negative real coefficients. I'm going to say it's log-concave if either it's identically 0 or as a function on the positive orthant, log of the polynomial is concave. Just as a sanity check, if it has non-negative coefficients and it's not equal to 0, then it defines a positive. It's positive everywhere on the positive orthant, and so it makes sense to compose with log. So what I want is that resulting function is concave on the entire positive orthant. And since we might want closure of a class of polynomials with respect to things like derivatives, I'm actually just going to enforce that we have that. So I'm going to say that a polynomial is strongly log concave if both the polynomial and all of its derivatives of f are log concave. And so here I am writing the shorthand. Di is taking the derivative with respect to variable x of I, and I'm allowed to do that any number of times with respect to any number of variables. And I always want the resulting polynomial to be log concave. It's a polynomial, so I'll eventually get down to 0, but you know, that's fine. And everything in between should be log concave. So this will often get abbreviated SLC if I'm short on space. And this turns out to be a sort of surprisingly useful class of polynomial. There are nice examples. So the generalized Brun-Minkowski theorem says that if I take n convex bodies in R to the D and I take their mixed volume polynomial, one, this is a polynomial, and two is that it's log concave on the positive orthant and that all of its derivatives are as well. A much simpler and easier to check example comes from a univariate real-rooted polynomial whose roots are non-positive. So let's say whose roots are all negative. And this we can check very explicitly. So if we take, how do we check concavity? We take log, we take two derivatives. If you take this polynomial written as such and take two derivatives, you get an expression as such. You get a sum of negative squares of rational functions whose poles are in the negative real line. And so in particular, this is going to be non-positive on the whole positive real line. And so this just shows that f, the polynomial itself, is log concave on the positive real line. And in fact, it's strongly log concave, because if you imagine, let's see, if you imagine we have f, it has a bunch of roots, and then we take its derivative. The roots, again, will all have to be real and they will have to interlace. And so in particular, if they were all negative before, then the roots of the derivative, f prime, will also have to be negative. And so we get a polynomial of exactly the same type. And so we can do exactly the same calculation and see that it's, again, log concave. I think I already had that picture. So then and we can repeat, as much as we like, and we continue getting log concave polynomials. And so this shows if you start with a real rooted polynomial like this, you end up with something strongly log concave. And this might seem a little niche, but in fact, this a multivariate generalization of this will give us a large and very nice class of polynomials of this form. Namely, so the big example is something called stable polynomials. There's a few different ways to define them, but the one I'll use right now is that it's sort of real rooted with respect to the positive orthant. So I'll say that a polynomial, I'll again always take it to have real non-negative coefficients, and it's stable if whenever I restrict to a line in the direction of the positive orthant, I'm imagining my direction is in the positive orthant and say through, oh dear, through any point I like, I will always get a univariate real rooted polynomial. So this picture, the polynomial is maybe a polynomial in two variables of degree 4, and whenever I restrict to a line, in any line I like in the direction of the positive orthant, I always find 4 real roots, and that's what independent. That's what the picture is trying to show. One can also define this in terms of the complex roots of the polynomial, avoiding points in the upper half plane. And a lot of the tools for studying stable polynomials sort of come from convex analysis, but for now we'll stay with the real numbers. So one can check, just like with univariate polynomials, that if you have a polynomial that's stable, then it will be log concave on the positive orthant. And also, just like the derivative of a real-rooted univariate polynomial is real-rooted, the same happens with stable polynomials. If you take a stable polynomial, you take a derivative with respect to with one of the variables, you'll end up with another stable polynomial. And so together, just like the univariate case, we see that we get something strongly log concave. So this is not the main object of the day, but this is a beautiful class of polynomials. One of the many nice things is that there are there's a powerful classifications of operations that preserve stability, that preserve this property. And so developed. So the seminal papers are by Bourget and Brendan from the early 2000s. And it also, distributions coming from such polynomials have lots of nice properties. One of them is something called negative dependence, where the probability that any 2 elements show up jointly in a set chosen corresponding to your distribution is less than it would be if it were independent. And just as a more general plug for stable polynomials, so they've shown up in the solutions of a lot of big conjectures in the past 10 or 20 years. So Marcus, Spielmann, and Srivastava used the theory of these polynomials and their operations preserving them to prove the Kadison-Singer conjecture and operator theory, and produced Ramanujan graphs. Leonid Gurvitz used this theory to give a proof of reproof of the van der Waerden conjecture on the bounding the permanent of the doubly stochastic matrix. And so it's a very rich theory that one has a lot of tools to work with. And in particular, this falls into the category of the polynomials of the day, which are strongly log concave polynomials. And part of this talk is to try and, or part of the project I'm working with my co-authors to extend this theory to this broader class. So one of the combinatorial objects that shows up in the study of stable polynomials is something called a matroid. Anyway, so we're going to take a little interlude and discuss what a matroid is, and they're going to turn out to have very close ties with this class of polynomials we're talking about. So matroids are a combinatorial object that tries to model various types of independence. So there's a formal definition that I'll give. So it's fundamentally a ground set, which I'm going to take to be the numbers 1 through n, and a collection of independent sets. So which is just some collection of subsets of 1 through n satisfying something. And the 2 things that we want them to satisfy is one, they should be closed under inclusion. So it should be a simplicial complex on 1 through n. And the other is a little more interesting, is that if I have two independent sets, two sets I'm calling independent, and one is bigger, I should be able to pick some element from the bigger one and add it to the smaller one, so that the result is still independent. Okay, so that's the sort of formal definition. Okay, there's all sorts of terminology one could associate to this. Because it's a simplicial complex, we can take elements that are maximal under inclusion, we'll call those bases of the matroid. And this second criterion means that all of those will have the same size, and we'll call that the rank of the matroid. And a lot of the language comes from trying to model linear independence of vectors. And so one of the easiest examples is if I take a collection of vectors in some vector space, and I just record what subsets of 1 through n correspond to linearly independent vectors. And the maximal ones will be those subsets that form a basis for the span. They'll all have the same size, and that size will be the dimension of the span. So just as an easy example, if I put 4 vectors in R2, sort of generically, then any 2 of them will form a basis for the space R2. And any subset of size at most 2 will be linearly independent. And so in this case, I have a matroid whose bases are any subset of the numbers 1 through 4 of size 2. One of the appeals of matroids is that it doesn't just model independence of linear vectors, but also lots of other nice types of independence. So one might be interested in the cyclic independence of edges in a graph. Turns out they also satisfy these axioms. Or if I take an algebraic field extension and look at elements in it, then I might be interested in algebraic independence of subsets of elements. And just to finish with a non-example, so there are many non-matroids. For example, if I took the subsets 1, 2, and 3, 4, these will not be the bases of any matroid, because if they were, then I would need a subset of this basis 1, 2 would be S, would have to be independent. And I would have 3, 4. And the second axiom means that I would have to, this one is bigger, so I'd have to be able to take an element from the bigger one and add it to the smaller one to remain independent. But there's no way I can take one of these and add it to one to get something independent. There's at least some non-example. And in addition to modeling independence, there's a lot of reasons to like matroids. One can model the geometry of hyperplane arrangements. These are also sort of natural objects in which greedy algorithms work well in combinatorial optimization. Okay, so that's the primer on matroids. And the reason that they come up in this talk is that there's actually a very close connection between log-concavity as a function and matroids.
Cynthia?
Yeah.
Can you just explain what is cyclic independence in the previous example?
Oh, sure, yeah. So if we had, let's draw a graph. That's my favorite example. Suppose we had a graph with 5 edges. And so then I might be looking for subsets of the numbers 1 through 5. So here n is 5. I take subsets of these. And then, so subsets of edges with no cycles. So 1, 2, 1, 2, 3 is a subset with no cycles, but if I added 4 in, then that's no longer independent. And so in this case, the independent sets would be collections of edges with no cycles in them. And the maximal elements, if we have a connected graph like this, are actually the spanning trees. Yeah. Yeah.
Thank you.
Okay. Yeah. Any other questions? So it turns out that if you have a polynomial of a certain form, so here I'm taking subsets of 1 through n, all of the same size, d. If you have a polynomial with this support that has this property of being strongly log concave, then the subsets that show up with non-zero coefficients are actually have to be the bases of some matroid. So this property of strong log concavity actually enforces this matroidal constraint. And the harder thing to show is that actually all matroids show up this way and show up with sort of the coefficient 1. So if I take any matroid and I sum over all of the bases and just sum the sort of corresponding square-free monomial, the resulting polynomial I get is strongly log concave. And so this has been proven now several times by several groups of authors. So in addition to us, so Peter Brandin and June He showed this using the closely related theory of something called Laurencian polynomials, sort of turn out after the fact to be the same as strongly log concave polynomials. And it was also proved using sort of different methods by Bachman, Ern, Simpson recently also. And one of the reasons that there's sort of all happening right now is that it's really building off of some of the sort of breakthrough work by Adeprecito, Hu, and Katz in 2015 on sort of combinatorial Hodge theory. So that's sort of how the big confluence of results has happened. But so the main takeaway is that this property of log concavity and matroids are much more closely related than a priori they have any reason to be. Okay. And so I want to digest this property of log concavity a little bit. And so
I have a question. So
yeah.
This means that the strongly log concavity has a much simpler or cleaner description than stable polynomials, right? We don't know. You mentioned theorems which preserve stability, but classification of polynomial stable in other terms, like the Lax conjecture, which answers it for few variables.
Yeah.
But for several variables, as far as I know, maybe there's some conjectures, right?
Yeah. Yeah. So it's a lot easier to test strong log concavity for sure. And also the first part of this statement, is true for stable polynomials and was known previously. And there's a lot of work trying to figure out sort of what matroids come this way, either with coefficients 1 or with some coefficients. And it's really a mess. Like it's really hard to.
So I'm a stable polynomial or hyperbolic. I'm mixing them up. That seems to be a more complex notion, given this beautiful theorem of yours. Yeah.
Yeah. In terms of the. Yeah. I think it's more. It's more difficult to test. It's more difficult to. But you get some things. So like negative dependence, for example, you get sort of. And isn't true for all matroids, so it's sort of it would be hopeless to begin with. But yeah, so yeah, it's much easier to test this, which one could view as an advantage or not. Like maybe you lose some richness of description, but you can at least test them.
Yep. Thanks.
Yeah. So let's what are we doing? We are going to digest a little bit this property of log concavity. So if we have we have log concavity of f at some point, and we just do the multivariate variable calculus exercise, we write down the Hessian, we evaluate it at this point, and the resulting matrix should be negative semi-definite. All of its eigenvalues should be negative. And if you actually evaluate, just write out what the Hessian is, you get and evaluate at this point, you get f, which turns out to be a scalar, times the Hessian, which is some matrix, minus sort of the gradient times its transpose, which is a rank 1 matrix, divided by some positive number. Okay. And so what the takeaway is that we have a matrix with non-negative entries minus a rank 1 matrix is negative semi-definite. And so I claim that means that the Hessian of f has at most one positive eigenvalue, because on the orthogonal complement of the gradient on a hyperplane, it has to be negative semi-definite. So here I've tried to draw the zeros of this quadratic form of the Hessian. It's going to have to be positive on the positive ortho, and I'll have to take negative values on the orthogonal complement of this gradient. Okay. So just an example. This is sort of the basis generating polynomial of the matroid I got from those four vectors in the plane. Every pair of the numbers 1 through 4 shows up. And if I take its Hessian, I get just the all ones matrix minus the identity. You can check that this has exactly one positive eigenvalue as promised, corresponding to the all ones vector. If we were to take the polynomial corresponding to the non-matroid that I gave you, what we get is I get a block diagonal matrix. So we have little 2 by 2 blocks. And so in particular, it's going to have 2 positive and 2 negative eigenvalues. So that's out. Yeah, and this property of having one positive eigenvalue is sort of useful in various ways. One of them is that you can actually use it to understand the shape of this distribution a little bit. And the sort of univariate example of this is that if you had a strongly log concave polynomial in homogeneous in 2 variables, it's fairly restrictive, then it actually the coefficients have to satisfy Newton's inequalities, so they have to be ultra log concave in the discrete sense, and there's sort of multivariate versions of that. And so in some sense, if one way to think of the theory of stable polynomials is if you want to show univariate polynomial is real rooted, one could, take some multivariate generalization of it and sort of get to it, start with something you know is stable and get to it through some long process of operations. So this theory of stable polynomials might be like a machinery for showing real rootedness. And I think the theory of strongly log concave polynomials could be a tool for showing discrete log concavity. Okay. I want to talk very slightly about the ideas that go into the proof of this. Sort of my favorite lemma from this, which is not too difficult observation. Is suppose you have 2 quadratic forms on Rn, and they take positive values on the positive orthant, and they're negative values on some hyperplane. So in particular, each of these individually can have at most one positive eigenvalue, because otherwise the negative eigenspace would intersect this hyperplane. The positive eigenspace would intersect this hyperplane H. But also both of the conditions that I've written down are true for then any convex combinations of Q1 and Q2. So if I take some non-negative combination of them, then the result will be forced to still be positive on the positive orthant and still be negative on this hyperplane. And so in particular, any convex combination will also have this property of having only one positive eigen. And so this sort of gives a method to test sort of finitely many things, like quadratic forms, and then conclude things about their convex combinations. That's a sort of high level idea. Okay. And so to actually be able to state a theorem, what I'm going to do is to a polynomial, I want to associate a graph whose adjacency matrix is the Hessian, say evaluated at the all ones point. So just as an example, if I took this, the elementary symmetric polynomial that I've been doing so far, this would just give me the complete graph. If I took the non strongly log concave polynomial, this would just give me a disconnected graph. And I forget all the weights. I throw away, I keep only the discrete information. I'm really just asking what pairs of variables sort of show up in a common denominator. And if I do this, then we get the following characterization of strongly log concave polynomials, is that if I start with something that's homogeneous to some degree, then I can test if it's a polynomial strongly log concave by checking that the graphs I associate to all of the derivatives are connected just as a graph, and that if I take derivatives, enough derivatives to get down to a quadratic polynomial, then the resulting quadratic form has only one positive eigen. And this picture is somehow is attempting to suggest the proof of this is that if I have some connectivity, then I can sort of exploit this taking convex combinations of things. And these are sort of the extreme things that one would want to take for convex combinations. But so in particular, this is a fairly testable condition. And we see.
Sorry, I assume this is then very closely connected to the definition of Laurencian. Yeah.
So these turn out to be the same, just identical. So this is just the exact same thing. I mean, there's
so that's a definition of a Laurencian polynomial.
Well, okay. So it turns out, so the way that they define Laurencian is they define an open set of polynomials where this is all sort of strictly where you forget one.
Mm-hmm. Right. So up to that closure point. Okay.
Yeah, but then it turns out to be the same. So it turns out to be spot on the same, but it's like you need some proofs. yeah, it's really the exact same class of polynomials as the Lorentzian polynomials studied by and again, these are really both trying to distill some of the properties that were in this paper by Adeprisuto, Hu, and Kat.
You mentioning that paper, can I ask, you said it was motivated, the main theorem you put up earlier.
Yeah.
Was motivated by that paper, but does it actually use the results in that paper, or was it independent?
No, it's independent.
Okay.
So it's
so you don't need to use any of the Hodge theory.
No.
Okay.
Yeah, I mean the Hodge theory. If you try and if in your personal tastes you don't like, let's say you're crazy and you don't like Hodge theory, you just don't want the consequences. The relations that show up are you have a quadratic form and you want it to be, and it's negative semi-definite on some hyperplane. So that's when you dig into the Hodge-Riemann relations, in the first level of the Hodge-Riemann relations. That's the thing you find.
Okay.
And so yeah, if you try and simplify that, this is sort of what you end up with. And however you go about defining it, this is sort of the class of polynomials that you end up with. And the ring, I mean, one could, if you really wanted to go the Hodge-Riemann route, you're sort of looking at the polynomial, let's see, the ring of differential operators, mod the apolar ideal of F, mod the ones that kill F, the polynomials of delta F equals 0. And that's sort of the ring that one would do, the algebra that one would do the Hodge theory on. But you don't need any of it. That's sort of the connection, but all the proofs in this are sort of self-contained.
Okay, thanks.
Thanks. And then so the other sort of nice connection that these things have comes from really thinking about these graphs and the sort of corresponding adjacency matrices. So if you had a non-negative matrix, one natural inclination might be to try and turn it into a Markov chain. Try and rescale, say, the rows so that they all sum to 1, and then look at this as a transition matrix. So for example, if we started off with a log-concave polynomial, we could do that. We could get a matrix with non-negative entries, like taking the Hessian and then evaluating it at the all ones point, for example, and then scaling it by some diagonal matrix with non-negative entries, so that we get so that it becomes stochastic. And then it turns out this so doing this won't actually change the signature won't mess with the signature of the matrix. And so what you end up with is you end up with a stochastic matrix whose second eigenvalue is still negative. And if you Lazify the corresponding random walk, then you conclude that its second eigenvalue is at most a half, just trivially. So for example, if we take the elementary symmetric polynomial and we take its Hessian, we can rescale so that I mean, this is symmetric all the coast. Here it's doubly stochastic. And then we can Lazify this. And what this does is, so this gives us some random walk on the numbers 1 through 4. And one way to view this random walk is that if we start with some element, say I in 1 through 4, then we pick a basis that contains I. Here, there will only be 3 choices here of what element to add, and then we could remove, to get back to a singleton, we could remove some element from that basis. And so then what happens? So we have, for all of the, if I start with 1, for example, then I have 3 choices of an element to add, and I add each of them, say, with probability 1/3. And then of those 2 elements, I remove 1 at random. And what I'm going to get is I have a half chance of, I have 3 ways of just getting back to the element I started with. And then I have a 6th chance of changing. And so that's exactly this is exactly the probability transition matrix for this block. And it turns out that sort of relationship between the Hessians of these polynomials and various random walks sort of generalizes. And one can use this to look at transition matrices of walks on much bigger spaces. So getting bigger, if we took some simplicial complex, pure of dimension d-1, so some collection of subsets closed on an inclusion where all of the maximal ones have the same size, d, then, and I'm going to assign some non-negative weights to the top dimensional faces. And what I can do is define a random walk on the faces of a given size in the following way. I can define sort of 2 different Markov chains on sets of a given size. And one is I start with a set of a given size, and then I uniformly at random kick out one of the elements. And then I need to get back up to size k. So I'll add in one of the elements, and I'll do it sort of with probability proportional to whatever the corresponding weight is. And then, I could continue. And if I just, view these 2 as a single step, then this gives me a random walk on things of size k. I could also, do the other way around, right? As I could also start, assuming that I'm not at the top level, I could start as we did here. I could start at some point, at some set, add an element I'm allowed to add with some probability, and then boot out an element uniformly at random. So I also have sort of a walk I can consider going this way. And it turns out that one can, because you're sort of composing 2 walks in different orders, one can have a very precise relation of the eigenvalues of the transition matrices for the sort of walk you get going up and down and the walk you get going down and up. And also the walk you would get, oh, that's an eraser. No, sorry. The walk you would get, going this way also. One can precisely bound what happens to the eigenvalues of all of these things. And the, somewhere in this are the transition matrices look like sort of lazified, look like the Hessian, things you get from the Hessians of your polynomials and its derivatives. Yeah, and so the other sort of big thing this theory ties in with is the theory of high dimensional expanders, which is developed by many people. And the theorem that ends up being very closely tied with this theory is that if you have a simplicial complex, a weighted simplicial complex, and all of its, it has some combinatorial property, namely all of the k-dimensional links have a connected one skeleton. So some graphs are connected. And all of the sort of transition matrices you'd get for certain walks on the one-dimensional links have second eigenvalue at most 0. And so one should think of these as both sort of local criterion. Then what you get is that the transition matrix for the walk on the top dimensional faces, which is, you know, a huge, like n choose d size random walk, its second eigenvalue is bounded away from 1, is at most 1 minus 1 over d. And you know, so this is in particular nice because bounding the second eigenvalue away from 1 means, you know, gives you results on how fast the Markov chain will sort of converge to the its stationary distribution. And so hopefully this looks a little bit familiar. So it turns out that that if you have some weighted simplicial complex, this is the exact same thing as the sort of generating polynomial for this thing being strongly log-concave. If you sum over all of the top dimensional faces, the weight, and then the corresponding monomial, then the condition, then these two conditions are equivalent to it being strongly log-concave. And so in particular, you know, this means that you can run a Markov chain on the basis of a matroid this way, and it mixes, you know, relatively quickly. So this was sort of proved and maybe improved by another group using kind of different methods. And then my co-author is also talking in the computer science discrete math seminar in a week, I think 11/15. So if you want to hear more about that, you can come to that. So yeah, so just to say that, you know, so that this property of being strongly log-concave also sort of ties in very nicely to this sort of pre-existing theory about random walks on faces of simplicial complexes sort of that will mix quickly. Okay, so just to finish up, so today is sort of a pitch for log-concave polynomials. There's lots of nice examples that one might care about that fall into this class. I didn't talk about this so much, but it's closed under on many operations that one might like derivatives, for example, conditioning. It has some strong combinatorial implications, like the support being a matroid if all your monomials are square free, or discrete log-concavity of the coefficients if you're sort of bivariate. And it also, you know, like stable polynomials sort of give distributions that maybe with some asterisks can be efficiently, approximately sampled using a Markov chain. And so these are the sorts of, you know, things one might like from such a class. There's lots of, there's still lots of open questions sort of in this area. There's lots of other parts of the theory of stable polynomials that seem like they may or may not extend to this and would be useful. For example, a classification of operations that preserve this property. There's also a whole convex programming story associated to stable polynomials that, you know, may or may not extend to sort of this generalization. And then from the combinatoric side, there's, I think it'd be very nice to try and extend this story to other combinatorial objects beyond Matroids, necessarily having to sacrifice, some of the bounds that you would get that show up. But for example, jump systems would be a natural generalization. Coxeter Matroids would be great, although we don't know quite how to do it. But that's sort of some of the open questions in this area. And that is all I have. So thanks. Thank you for your attention.
Well, that's great. Thank you very much. You were a wonderful, wonderful lecture. If people want to unmute themselves, they can applaud. Thank you. We have some time for questions.
Yeah, we are.
I wanted to ask about a specific action. What happens if you start with a stable polynomial, or say a specific family of stable polynomials, under the action of just putting one in one of the variables? Like,
yeah, that's.
It's resembled to the taking derivative, but it doesn't kill everything.
Yeah, and so that this is what you're talking about, right?
Yeah, exactly.
Yeah, that's so that if f is stable, then this will be stable also, and because you're really in the picture. Let's see if we can draw the picture. Have like the orthant, This was the picture I wanted to draw of the variety of f.
We're still in R plus.
Yeah, and so the
R plus of this is embedded in the R plus of the bigger one.
Exactly. Yeah. And in some sense, this is you're restricting to well, at least in this picture, you're restricting to a line that's in the direction, at least the non-negative orthant.
Yeah, you can do any line in that direction.
Yeah, you can. Yeah, exactly.
I mean, in the, I don't know whether the theory, I think, originated in proofs of the Li-Yang theorem, which are polynomials in one variable which are real rooted, but which are most easily proved to be real rooted by separating the variables out in the definitions and proving that the several variable thing has this property, and then making all the coordinates equal.
Yeah, it's the same thing is true for like the matching polynomial, but polynomials counting sort of matchings. It's remarkably effective to start with a univariate thing that you don't understand, turn it into a multivariate thing, and then do stuff with it, and then restrict back. That is I still find surprisingly effective.
Simply talk because.
I have a question. So if you take a special matrix like the one for spanning trees of a graph, does the polynomial tell you anything about the graph?
Does the polynomial tell you anything about the graph?
Some matrices are really special, like spanning trees.
I mean, well, it tells you all of the spanning trees of the graph. I mean, so those are actually, so that polynomial that you would get, so just sum over like T spanning tree, like xt, that by the matrix tree theorem, this is, you can write as sort of the determinant of, well, some matrix where some, like summing over all the edges, x, e, a, e, where these matrices are actually positive semi-definite. And it's very explicit. I'm lazy. Okay. And so these are actually stable. And so, for example, you can show that this satisfies this negative dependence property. That if you take a graph, let's choose this graph, and you pick say a spanning tree uniformly at random, And then you look at, maybe you have some edge, you have two edges, and you look at, well, what's the probability that my edge I shows up versus the probability that, J shows up in my randomly chosen spanning tree. This satisfies this negative dependence property, that the probability of both showing up is less than it would be than the product of the probability. And that I'm sure there's other proofs, but that's an immediate consequence of like this polynomial being stable.
Stable. Oh, neat. Okay. Thanks.
I wonder, may I ask you, it looks like you are starting with a polynomial and eventually you associate some simplicial complex and this high-dimensional expander.
Yeah.
What about going back? You hinted some application to sampling theory that at the very end you said something.
Mm-hmm.
If one come up with some kind of a better high-dimensional expander, does it help you to get some better sampling?
You'll have to tell me sometime what you mean by a better high-dimensional expander.
For example, I mean, I kind of look a little bit in those papers which you mentioned, and they usually not bounded degree or, and I think you can achieve just as good method by bounded degree Ramanujan complexes, kind of using some more fancy stuff, and I just wonder if it's of any use. At some point you wrote sampling.
Yeah, well, so sampling here, I mean, means approximate sampling, means running a Markov chain until it gets sort of close enough to the distribution that you want. So that's what I mean by sort of, how this might give a sampling algorithm. Yeah, I mean, I think the short answer is I don't know. All of the things that I personally know how to do is try to control this, bound this second eigenvalue away from one. Yeah, I think the short answer is I don't know, and maybe we should have a longer conversation.
Okay.
Any other questions? I'd like to thank the speaker again for a beautiful talk. Thank you very much.